All right, guys, let's talk about binary ionic compounds. I gotta say right off the bat that this topic is really critical to understand. So much of what we do in chemistry depends on you understanding how to put together compounds, what ionic compounds are, and it's just a very important topic. So please pay close attention here. Okay, so a binary compound is made of two kinds of ions. The first kind is a metal, and the second kind is a non-metal. Okay, so any compound that combines one type of metal with another type of non-metal is thought to be an ionic compound. And so how do you know what's a metal and what's a non-metal? Well, in the periodic table, you'll notice that there's this kind of thick, chunky, stair-steppy line here, okay? And that's a really important place to understand what this thing means. So everything that is on the left of that line, which is the majority of the periodic table, it actually includes this stuff down here too. The majority of the stuff here is metal. Okay, now it's only this neighborhood over here in the upper right-hand corner of the periodic table that are nonmetals. Okay, so any element symbol that comes from the left of that line, the stair-steppy line, combined with another elemental symbol from the right of that stair-steppy line, that's going to be an ionic compound. And the reason we call them binary ionic compounds is that just means that they're two-part compounds. It doesn't mean there's only two atoms, but it just means there's only two types of symbols, okay? So a metal combined with a non-metal is an ionic compound. All right, so here's some examples of ionic compounds. These are the formulas that you'll get pretty familiar with these actually. So here I'm gonna underline the metal with the red pen here. Calcium, lithium, copper, iron, zinc. These are all the metal parts of the compound. And then the other part is the non-metal. See, chlorine, iodine, oxygen, sulfur, nitrogen, oxygen, and phosphorus. Those are the non-metal parts. So when you see a formula made from something from over here, which is most of the periodic table, and then the other symbol comes from this neighborhood, that is an ionic compound. All right, so let's determine. One of the skills you need to know is what compounds are called. Okay, and so let's learn how to name some of these ionic compounds. And the first thing to know is that the subscripts that you see in these formulas, they are not going to have anything to do with the name of the compound. Okay, so you don't have to take into account, like down here, for example, the 3 and the 2. Those don't have anything to do with the name of these compounds. Okay, the metal that you have in the compound, we just call it by the same name as its element name, and then the non-metal name changes its ending from whatever it is as an element to the letters IDE. Okay, and we'll do some examples here. So let's just run through that same list here. This is a compound you're probably familiar with. So the metal just keeps its elemental name. This is sodium. And then chlorine changes to chloride. See that IDE at the end there? A chloride is what you would call chlorine as an ion. So the metal stays the same, the non-metal's name changes its ending to IDE. So this one would be magnesium. What do you think? Iodine changes to iodide. Okay, this one, calcium. Oxygen turns to oxide. Lithium. Sulfur changes to sulfide. Copper, that's the symbol for copper, Cu. And then phosphorus changes to phosphide. Here's one, iron, Fe is iron. And then this oxygen turns to oxide. And then here, this symbol is zinc, it's a metal. And nitrogen is the nonmetal. Nitrogen's name turns to nitride. Okay? Now, it's really important to know that when you are writing a chemical formula or making a formula into a name, that you always have to put the metal element first. Okay, you would never want to say like chloride sodium or something like that. It's got to be the cation, which are the metals. They're the ones that have lost electrons, and then the anions, which are the nonmetals, which have gained the electrons. Okay, so that's how you name ionic compounds when you see them. And now let's figure out how we make up these formulas, because that's a very, very important part here. So formulating ionic compounds. So if you have the symbols, you can do this. Formulas may or may not have subscripts, and so like in the examples we just did, we had some of our formulas did not have subscripts, like NaCl, no subscripts. CaO, no subscripts, but you know, some of them do, like, and why are those there? That's what we're going to try to figure out, because understanding how to get the right subscripts in place is really, really, really important as we move on in chemistry. And you just really can't move on very well without knowing how to do this next part. So please pay attention. Okay, so when we look at our periodic table, the periodic table is really, really nice. We've talked a little bit about this in our ionization video. Remember that H, L, I, and A. Remember these elements on the far left of the periodic table, they all tend to lose their one valence electron. And when you lose an electron, the symbol is also tagged with an oxidation number. Right? And the oxidation number, if it's positive, that indicates the number of electrons lost. And because all elements in a column are going to behave the same way, we can say that all of these elements in this column have a positive 1 oxidation number. Okay? Magnesium and calcium and so on down the row here, they tend to lose 2 electrons, and they become a positive 2 oxidation number. Okay, boron, aluminum, and so forth, they lose 3 electrons, and that column has a positive 3 oxidation number. And this 14th column, we're kind of forgetting about that for now. But let's jump ahead here to the like nitrogen and phosphorus column. These guys will gain. And just as a quick review, remember that when you see a negative oxidation number, that means we have gained that number of electrons. So nitrogen and phosphorus, they try to gain 3 electrons to become stable. The oxygen and sulfur group here, these guys try to gain 2, and they have a negative 2 oxidation state. And then this last column here, the fluorine, chlorine, bromine group, these guys will tend to gain just 1 electron and become a negative 1 oxidation state. Okay, so knowing the oxidation number of the element that you're trying to put into a formula is really, really, really important. And here's how those work. We follow something called the old switcheroo rule. Okay, and the switcheroo rule is really, really easy to follow. The oxidation number of the metal, which is the positive number, by the way, becomes the subscript of the nonmetal, okay, which is the negative part of the compound. And then the oxidation number of the nonmetal becomes the subscript of the metal. And you know, I'm going to do some examples here just to make sure you're on pace. So calcium, again, calcium comes from this positive 2 column of elements. So we can say pretty definitively that its oxidation number is positive 2. Phosphorus, on the other hand, comes from this -3 column here, so its oxidation number is -3. So what we're going to do is take the number. We don't care so much about the positive or negative, but we want to take the number of the oxidation number and pull it down to make it the subscript of the nonmetal. And the 3 of the nonmetal becomes the subscript for the metal. Okay? So when you move those numbers around, you get a formula that looks like this: Ca3P2. And the reason we're trying to do this is because these compounds must be neutral. Neutral is good when we're talking about compounds. Neutral is not so good when we're talking about atoms, remember that. But here's why it becomes neutral. If we take our 3 calciums that each have a charge of +2, if we multiply the number of calcium atoms by the charge, we get a +6, right? And we're trying to counter this with our 2 phosphorus atoms, which each have a -3 charge, oxidation state that is, and our 2 times our -3 gives a -6, oops, -6, not 3, 6, and then the sum of the positive and negatives is neutral, and that's good. Okay, now that's just sort of why we do it. As long as you can execute this switcheroo rule with oxidation numbers, you're in good shape. Now, if the oxidation numbers match up, then you don't need any subscripts. So for example, sodium, which is over here in the +1 column, it is matched with chlorine, which is in the -1 column. And so here's the oxidation states, they're both 1s. And so when the positives just equal the negatives, you don't have to put a subscript. So no subscripting here. And that's actually true if your oxidation numbers are 2 and 2 or 3 and 3 as well. So here's magnesium, +2, oxygen, -2. There's no need to cross these because they already cancel each other out. And same with the +3 and -3 with aluminum and nitrogen. See how that works? Okay. All right, so now we move on to some more complicated stuff. And this is something you'll work with a lot here. These are known as polyatomic ions. So these, by and large, are anions, okay, with negative oxidation numbers, just like the anions from the right side of the periodic table, okay? The only difference is that they have multiple elements and they have a chemical formula. And that entire chemical formula has its own oxidation state. So for example, this thing here, NO3, this is known as nitrate. And nitrate has an entire oxidation state of -1. All right, same with this guy known as acetate, hydroxide, bicarbonate, and cyanide. And there's a list of these that you'll be provided in class, so you won't have to memorize these. You can always look these up. These little formulas here all carry a -2 oxidation state. This is carbonate, chromate, sulfate, and silicate. And then these, there's only a few of these actually with a -3, but this is called phosphate, and this is called citrate. Now, the one oddball that you're gonna run into is this guy called ammonium. And ammonium is a polyatomic ion with a +1 oxidation state. And that's different because it's gonna be at the front of a chemical formula instead of at the rear of a chemical formula like these negatives would be. Okay, so let's do some examples with polyatomic ions, and then we'll be done. So, first thing to know though is that polyatomic ions, they very rarely end with the letters IDE. In fact, this whole list, I think I went through these, the only one that ended with IDE was hydroxide, oh, and cyanide does as well. But almost all of these end with ATE, like ate, like nitrate, acetate, carbonate, chromate, sulfate, and so on. And so that word ATE, or the ending ATE, or possibly ITE, those should indicate to you that you're not dealing with a monatomic ion from the periodic table, you're dealing with a polyatomic ion from this list of polyatomic ion formulas. Okay, so let's take a quick peek here. So let's say that we want to make a compound called sodium phosphate. So we take our symbols just like we did before. Sodium's symbol is Na, its oxidation state is +1. Phosphate, that comes from this list of polyatomic ions here. Phosphate has a formula of PO4. It's got an oxidation state of -3. And it's just the same way that you did it the first time. You take the number of the oxidation and you make it the subscript of the other part of the compound, okay? So when you move this 1 from sodium down here to a subscript on the phosphate, and then you move the 3 oxidation state to the subscript of the sodium, you end up with this formula, Na3PO4. And notice that 4 is not a result of moving any oxidation states. That is just part of the formula for phosphate polyatomic ion. Okay, so there's room for confusion here, but you got to kind of start to see these polyatomic ion formulas for what they are. Now, here's an example where we have the need for parentheses. So let's put together aluminum carbonate. So we're going to do the same thing we did before. Here's the aluminum and the carbonate oxidation numbers. We're going to follow the switcheroo rule, and we're going to move the oxidation numbers into the subscript position. And then what we end up with is something that looks like this. Now this is incorrect, because this would maybe tell you that you have 2 aluminum atoms, 1 carbon atom, and 33 oxygen atoms. So if the polyatomic ion, requires a subscript, this is where your parentheses come in. And you have to separate the new subscript that is the result of the switcheroo from any subscripts that might be present in the chemical formula for the polyatomic ion. Make sense? So maybe we'll just do a couple more practice problems just to really solidify us here. So let's start off with knowing the formula and move toward a name. These are the easy ones, right? So here you just use the elemental name for the metal, sodium. And we know that this is not a polyatomic ion. This is just fluorine from the periodic table. So we turn that to fluoride. Okay. Magnesium. Chloride. So if it's only an element symbol at the back end of the chemical formula here, if it's just a single symbol, even if it's subscripted, but if it's just an element symbol, then it's going to end with the letters IDE, right? This is where we start getting into a polyatomic ion, and you name these the same way. Aluminum. But here's where it's a little bit different. Instead of changing sulfate to sulfide, remember the name of this polyatomic ion is sulfate, and it stays the same when it's part of a formula. So this is just sulfate. So we don't change the name of the polyatomic ion. Got it? How about this one? Calcium. Remember what this one's called? Phosphate. Good. Okay, now I think the harder way is to go from the name of the compound to the formula of the compound. So when you have the name, just start with your symbols. K for potassium, nitrate, because it ends with ATE, we have to look to our list of polyatomic ions, where did I put those? Here it is. So this one's called nitrate. Okay, and you'll again have a list of these. So don't just think that this is nitrogen. If it ends with ATE, it's a polyatomic ion. So NO3. And then you want to identify the oxidation states, +1, -1, and these don't have to cross, so this is just KNO3. Okay. Lithium bromide. So right off the bat, the IDE at the back of the name here should tell you that this is not a polyatomic ion. It's a monatomic ion right off the periodic table. Li +1, Br -1, and bromine, bromine comes from the -1 column here as well. And again, they equal each other, so there's no need to switcheroo. So this is LiBr. How about ammonium phosphate? So ammonium was our little oddball over here. Ammonium is a polyatomic ion. It's the only positive polyatomic ion that you'll ever deal with, and it's got a formula of NH4. So this is NH4 with its +1 oxidation state, and phosphate is PO4 with its -3 oxidation state. So now these don't match up. We've got to do a switcheroo, and this is now NH4 in parentheses with the 3 subscript from the phosphate. See how that works? And then our PO4 does not need a subscript because that number is a 1. All right, and last one, and then I think you probably got it. Sodium sulfide. So again, the IDE tells you that you're looking at an element symbol from the periodic table. Sodium, Na, +1 oxidation state, and sulfur. Remember, sulfur is right under oxygen in the -2 group, so its oxidation state is a -2, and we do have to switch because the numbers don't equal, and this is Na2S. Okay, and we'll do lots and lots of practice with this in class, but this again is really critical that you know how to do. So thanks for hanging in there. Hope it helped.